All right. So now that we've kind of talked about our different types of reactions, we're on to our fifth unit, which is all about reaction rates. Okay, so this is kind of our first pieces here now of describing the mathematical relationship between and measuring these reactions. Okay, so first off, we need a definition of our reaction rate, and we're going to say that the reaction rate is just the change in a concentration of one piece over time. Okay, so if I were to have this reaction here, right? This is a totally theoretical reaction, and I would say that my rate is going to be, right, the loss of A over time, right? So the loss of A, I would say, is going to be the negative of the change, of the change in the concentration of A, okay? So these brackets here, right, this is a representation of my concentration, and so my rate is going to be the negative change in the concentration of A over the change in time, okay? But if I wanted to relate this to my other pieces, right, I would need to relate it using the stoichiometric coefficients. So the stoichiometric coefficient for A here is lowercase a, so I would put that down in the bottom out front, okay? But this rate is going to be equal to the loss of B in my reaction, and it's going to have a stoichiometric coefficient of lowercase b over time. But this rate is also equal to how much of C I'm getting, right? So this is now positive, the change in the concentration of C that gets produced over the coefficient per time. And this is equal to the change in the concentration of D over the stoichiometric coefficient per time, right? So each of these, right, are describing this rate of this whole reaction. That's why we have to divide by the coefficient, because maybe it takes 3 A molecules to get this whole reaction to go, okay? That's why we divide by our coefficients there, all right? And so what we do is maybe these different pieces, one of them is colored, one of them's not. Maybe one of them has a certain molecular property that we can measure, okay? And we're going to measure those properties, and we can then measure the change in that property, and that's going to tell us the change in our concentration, okay? And overall, our rate is always going to be experimental, okay? Because it depends on the reaction conditions. So if it's going to be experimental, right, what we're going to want to do is we're going to use a method of initial rates, okay? And we're going to have to measure those concentrations, all right? So we'll see this in the lab, why we use the method of initial rates, okay? But let's talk about some of these reactions now, okay? So generally, right, first off, what we want to do is just be able to write the rate as it is changing something over time. But once we kind of understand that, right, that's really the basic piece, we want to be able to write the rate law, okay? So the rate law is essentially something kind of like this, okay, where we have rate equal to K times the concentration of A to some power. So in this, K, lowercase k, is going to be equal to some constant, okay? And this is going to take into account different temperatures, different, whether or not we've got a catalyst in there. It's going to take into account a lot of different pieces that are going to affect the rate, but aren't going to be directly influencing the reaction or not actively participating in the reaction, okay? So this constant, that's just K, all right? But then we're also going to have this m up here, this exponent, okay? And this exponent is really important, okay? And so let's talk about here where we have A going to products. All right? As A goes to products, right, it's going to have a rate law equal to some constant times the concentration of A to this power of M. And this is the reaction order. Okay? So if our reaction is a first order reaction, that means that we would have a 1 up here, and we would say that our rate is going to be linearly changed based on what our concentration is, okay? So if we have a 0 order, right, that's going to be no change, right, and no effect on the rate based on concentration. We can have first order, which is going to be linearly proportional. And then we can have second order. Second order, right, this would be a quadratic, and it's going to be squared, okay? So with this, I'm going to show us something from our textbook to help illustrate this, right? If I have, oh, I got to go one more page here. 2 more pages, rather. If I have this reaction here, where I'm on page 289 in our textbook, where I have CH3CHO, right, going to CH4 and CO. If I look at the different rates depending on the concentrations, I can see, right, here I've doubled my concentration. If I double my concentration, my rate doesn't actually double there, right? I go from 0.2 to 0.4, my rate does not double. It goes from 0.34 to 1.4. So that is not going to be first order. Is it going to be 0 order, right? 0 order would mean that as I double my concentration, nothing happens to the rate. No, something definitely happens to my rate. So in this, right, 0.2 to 0.4, I've doubled my concentration, but my rate has actually quadrupled here, okay? So this is what we need to be able to do, is we need to be able to look at a table like this and identify spots where our concentration has doubled and then see what happens to the rate, okay? There is also a mathematical way for us to do this if we don't have exactly double the concentration. We can compare 0.2 to 0.3. If we want to learn that mathematical representation, it is in our textbook, okay? So we can learn that. But I like just looking at the numbers there, okay? So oftentimes, right, these are the 3 that we are going to see in our class. We may, in reality, have half orders. We can have 3/4 orders, things like that. Things can get weird, but just in this class, this is what we're generally going to be seeing, okay? But this is for just one reactant. If we have more than one reactant, then we need to account for each of those reactants. Now our rate law is going to be rate equals K times the concentration of A to some exponent and the concentration of B to some exponent. And remember, these exponents come from experimental evidence, okay? It always comes from experiment, all right? But we can have the order with respect to A and that's going to be equal to M. The order with respect to B is going to be equal to N, and my overall reaction order is going to be equal to M plus N, okay? So let's again look at another example here from the textbook. If we look at the textbook, right, here we have a reaction between T-butyl bromide and a base, right, hydroxide, and we're going to get T-butyl hydroxide and bromide here, okay? So we have to do a few different reactions, and the first thing that we're going to do is we're going to change the concentrations of T-butyl bromide. When you do that, right, we're going to look at just these first two experiments, because between these first two experiments, we have doubled the reaction, right, or we've doubled our concentration of T-butyl bromide. When we do that, we look at the rate, and the rate has doubled as well. So that tells us that for T-butyl bromide, the rate is first order, okay, with respect to T-butyl bromide. So now what we want to do is we want to compare hydroxide. So do we have another one with the same concentration of this? Well, not at 0.5 molar, but at 1 molar, we do have some other experiments with the same concentration of T-butyl bromide. So now we can compare when hydroxide changes. So when hydroxide is 0.05 molar versus 0.1 molar, the reaction rate does not change. If the reaction rate does not change, even though we change the concentration of hydroxide here, right, that's going to tell us that we are zero order with respect to hydroxide, okay? So our overall rate law then is going to be right here, right, over onto the next page, where our rate is equal to K times the concentration of T-butyl bromide to the first power times the concentration of hydroxide to the zero power, right? So we can really write it just like that, okay? And this would even allow us to actually calculate K because we have the exact rates and we have concentrations. All we got to do is we got to plug in a concentration with the rate, and we can then calculate what K would be, okay? So we can calculate K here.